So thank you for attending this webinar dedicated to QSOC. So and thank you, Rosanna, for the introduction. So as already said, I'm working in the University of Liège on the QSOC classifier for Gaia. So this is the outline of the presentation. First, I will give a brief overview of what QSOC is doing actually. In order to better use the result of QSOC, I think the best way is to understand how it works. So I will describe the method I used. In this method, I'm using quasar templates. So I will describe how I'm building them and what is the use I'm doing for how I use this template actually. There will be a performance and result section, a recommendation how to properly use the QSOC results, so caveat and so on, and a future plan for the fourth and fifth Gaia data release. So basically, QSOC is designed to determine the redshift that I will classically call Z of the source that are classified as quasar by the discrete source classifier module. So despite its name, QSOC is not a classification module. It's instead rely on the COMBOB quasar probability that is derived by DSC. And we voluntarily selected a very low threshold of 1% actually. If DSC provides us probability higher than 1%, we will provide a redshift for this source. What is the implication of this choice is that we are processing a significant fraction of stars. We know it, and it is done on purpose. So QSOC is complete, but not pure. What is the reason behind this idea? Is that from a complete sample, we can draw a pure sample. So if you want to have a redshift for particular source, probably it is in the QSOC redshift. While if we had a pure sample, we cannot necessarily have this completeness. That's logical. Anyway, purity can still achieve using this class label, a pure class label derived by DSC, or there are also recipes that are given in the extragalactic content paper. So basically, QSOC is not doing classification. So this is not the goal of this presentation. This is only regarding the redshift determination. So how QSOC is working? QSOC is based on a chi-square approach that will compare the observed spectra that we see on the right plot, for example, set to rest frame, against a quasar template in order to derive the redshift. So QSOC is deriving a redshift in the range, would say 0.1 up to 6, roughly. And the right plot is actually quasar spectra that are set to rest frame once QSOC derived the redshift. So we can clearly recognize some common emission line from quasars. I'm also putting here the look back time. This was done for outreach actually. And this was an image of the week 2020. So as I said, we have the observation, we have the templates. Let's first have a look on how we derive the template. So the template is based on quasar from the 12th release of the SDSS quasar catalog from Paris-Séal. Actually, we selected 300,000 quasars, and we have to first extrapolate them to the wavelength range that is covered by Gaia. So in the plot below, we see on gray the SDSS spectrum. We are rejecting some border of the spectra because we have a lot of outliers in these ranges. And we can also see that in the SDSS spectra, we are missing the carbon-4 emission line. And actually, we are using a weighted principal component analysis method that we derived in this paper, 2015. And actually, we recovered emission line templates and continuum templates that allowed us to extrapolate the spectra. So we see that we are recovering the Lyman alpha emission line and also extrapolate the missing part. So for example, the carbon-4 emission line. Once we have this extrapolated template, we would like to convert them into simulated BP and RP spectra. For this purpose, we use the internal MEOG simulator that is closely related to the Gaia XPy tool. So this is something you can do at home, also converting spectral energy distribution into BP and RP spectra. So in this plot, we see the BP spectrum in blue and the RP spectrum in red. That's quite logical. And overplotted over the SDSS spectrum. This spectrum was selected on purpose because we have a lot of emission lines that are present in the spectrum, and we see that we can quite confidently recover most of these emission lines. Now, something that is annoying with the spectra is actually the fact that in order to do a proper cross-match, we have that the BP and RP spectra have bell shape, so meaning that the flux tends to zero at the border. In order to correct for this effect, we will divide each of the BP and RP spectrum by the BP and RP spectrum that would be obtained from a hypothetic uniform spectral energy distribution. So this is, for example, one of the spectra of high redshift quasars from the SDSS and still overplotted with the BP and RP spectra. And we see that actually we have this bell shape. Now, by dividing the spectra by what we call the flat spectrum, this is closely related to flat fielding actually. We are able to recover the overall shape of the spectral energy distribution. And also we are correcting for the different, actually in BP and RP spectra, the flux are integrated over wavelength bins of different widths. So this concurrently correct for this discrepant wavelength bin coverage, actually. And actually, we see in this bulk quasar that the overall shape is very nicely recovered. Still, we are not correcting for the different line spread function. Because this will be more complicated, and I will come back to this later. But we see this effect actually, flat filling. Once we have the unbanded spectra, we can then again use the method that was first used to extrapolate the SDSS spectra, but now in order to retrieve the dominant BP and RP components for BP and for RP. And here are the templates we are using in Gaia DR3. So those are pure emission lines templates, simply because I'm creating continuum before recovering the PCA component actually. And this closely match the templates that will be obtained from the classical composite spectra, Vandenberg and so on. So now that we have this template, we can think about using them in order to derive the redshift. I'm sorry, I'm drinking a little bit of water. So QSOC is based on the simple idea that the redshift, so relation between the observed and Western wavelengths of a given spectral features, this redshift turns into a simple offset if we consider it on a logarithmic scale. So notice here, the redshift will be a lowercase z, the logarithmic redshift, so this is this formula actually, will be the uppercase z in the rest of this presentation. So once we know that, it's quite simple to think that if we have Western templates and an observation vectors that are sampled on the same logarithmic wavelength scale, so where L is actually the logarithmic wavelength sampling and lambda 0 is the reference wavelength, then we would like to find the shift to apply to those templates in order for the template to match the shifted templates to match the observation in a chi-square sense. So here, the AGK are the linear coefficient that minimize this chi-square. If we know K, we can easily retrieve the redshift from this formula, simple formula. Anyway, this formula, although it's quite simple, it's quite complicated, time-consuming to compute, actually. This is a cubic time complexity. We showed in this paper that actually we can have a simpler computation using this formula, what we call the cross-correlation function. That is basically only a constant minus this chi-square. And in order to compute this cross-correlation function, it takes only linearithmic, so O n log n floating point operation in the order of. So this is the reason why we will now talk about the cross-correlation function, but this is clearly related to the classical chi-square, actually. Now, a little subtlety we have is that we don't have only one cross-correlation function in QSOC because we have BP and RP spectra that are disjoint. So actually, our cross-correlation function will be the sum of the cross-correlation function applied to BP templates and observation and RP templates and observation. But soon, for the simplicity, I will still use, for pedagogical purpose, I will use the cross-correlation function. So this may seem a bit complicated to understand on a lot of formula, and I think that the best way to understand is just to show a little movie applied to SDSS spectra. So in the spectra, we see in blue the observation that are shifted, and in orange the template. And we see that we are feeding the templates to the observation and computing the cross-correlation function. At the maximal peak, we then have the most probable redshift estimate, actually. So for the purpose of this observation, we use 15 emission lines templates and 5 continuum templates that are basically low order polynomials. In Gaia DR3, we only use 1 emission lines template and 3 continuum templates. I think this is more simpler to understand this way. So going back to this cross-correlation function, we'll have, as I said, that usually the maximal peak of the cross-correlation function corresponds to the most probable redshift. Local maximum, so for example, here in A, it's this one, corresponds to the fit of some emission features to the template, while local minimum will correspond to the fit of virtually nothing. Now, this is not always the case. So the maximum of the cross-correlation function does not necessarily correspond to the most probable redshift, simply because we may fit, for example, templates to absorption features and so on. So we have to use a more sophisticated way of choosing the optimal redshift. In order to do so, we use this score, actually, that is defined as a weighted norm, p-norm, actually, with two parameters that are given here, W0, W1, and the power here is this one. So this parameter are derived using a global optimization procedure, but I will not enter into the detail. I will rather concentrate on the chi-square ratio here and the z-score. Actually, what is the chi-square ratio? This is simply the value of the cross-correlation function considered at a given point divided by the maximum. So for example, here, point C will have a chi-square ratio equal to 1. While if we are going lower and lower, we will tend to 0. So it is comprised between, it stands between 0 and 1. And the z-score is actually a score measure that reflects the ability of the selected redshift to reproduce the expected emission lines. So I will spend some time explaining this formula because it is extremely useful and maybe a bit tricky to understand. So as a reminder, at a given redshift, actually, we are expecting some emission line to be present in the observed spectra. That's logical. How to check if we have effectively this emission lines? Then, for given redshift, we can put the spectra, the observed spectra, into a stream. Then have a look at the flux that is present at the expected the wavelengths where the emission line is expected. So we have this flux, E lambda, so this is this 8, along with associated uncertainties. And the idea is to have the product actually weighted geometric mean, and we can recognize this part as a cumulative distribution function of a normal distribution of mean zero and standard deviation sigma E lambda that is evaluated in this in E lambda actually. And we have the weight of the geometric mean that are provided here actually for BP and for LP. Now, if we have to summarize the z-score, if all emission lines are present where we expect them to be present, we'll have a z-score that is close to 1. While if we are missing a single emission line, then the z-score will quickly drop to 0, because this is a geometric mean, actually. So then this value is very important, just to see if we are efficiently recovering the emission lines. Now we are selecting what we think are the most probable redshift using the score represented, so that is based on the ratio of the maximal cross-correlation function of the cross-correlation function taken at the selected redshift divided by the maximum of the cross-correlation function and the z-score. Once we have this point, we are fitting actually a quadratic curves around this the selected peak. This can currently allow us to have a subsampling precision on the redshift, but also to derive the uncertainties on the logarithmic redshift. So basically, this is simply the asymptotic normal property of the maximum likelihood estimators that tell us that the uncertainty on the parameters, so here the K or Z, there is simply a scaling factor between them, is inversely proportional to the curvatures, the local curvatures around the parameters actually. What we have then, since the redshift is actually the exponential, the logarithmic redshift, we have that the uncertainties on the redshift is distributed as a log normal distribution. So it is normal if we take its logarithm, but it is obviously shifted by 1. What we have then is that the 0.16 and 84 quantile that roughly correspond to the classical 1 sigma limits are given by this formula. Right. Actually, the sigma z is retrieved from this fit of a quadratic curve. So now finally, we are also deriving flags telling us something may be wrong in this solution. So for example, we have the Z ambiguous flag that is telling us that at least 2 solutions have comparable cross-correlation function, comparable chi-square actually. So we have the uncertainty of choosing one or the other. Second flags tell us that the chi-square ratio is quite low actually, lower than 0.9. So meaning that probably we are not modeling the spectra very well. The Z-score flag is actually telling us that we may be missing some emission line. The not optimal flag just tells us that we don't know, we did not select the redshift associated with the highest cross-correlation function. And the final one is actually telling us that we are dealing with lower quality spectra. So meaning either it is faint, it doesn't have a sufficient number of transits, or a combination of both. So now you should have a quite clear understanding on the way QSOC is working. And we can go further and see the result we are producing. So basically, the QSOC results are published in the QSOC candidates table and consist in 6 fields. So the redshift, obviously, the uncertainty is lower and upper, so 16 and 84 quantile. The chi-square ratio, it has a name because I thought this is a cross-correlation function ratio. This will probably be changed in the future. The Z-score that is computed, and the flag that I just presented. One of the simplest ways to see if QSOC is working is actually to do a comparison against literature value. For this purpose, we did a cross-match, one arctagon cross-match against the MiniQuest 7.2 quasar catalog, considering only spectroscopically confirmed quasars, core-dominated type 1 quasars. And this yielded actually 440,000 sources common. And we are plotting on the right the logarithmic redshift error. Actually, why are we doing it? So remember that the logarithmic redshift, this is this formula actually. And we are comparing the one derived from QSOC to the one derived by MiniQuest. We are doing this simply because if we expand the redshift in terms of wavelengths, observed and expected wavelengths, we have a simple relation between the wavelengths of a spectral features we are expecting, so lambda true, but that we are misclassifying as another features that stand at lambda false. So meaning, by doing this, we have a clear view of misidentification between emission lines. Basically, if we are considering the right spectral features, then lambda true, this will be equal to 0. And this is actually the central peak. So this is on a logarithmic scale in Y. So we see that most of our predictions are correctly predicted. So basically, 68% of our predictions are correct. And we see that many mismatches between emission lines are occurring, and we can clearly identify them. We'll come back to them later. One way well, actually, we have a smooth background of wrong prediction. In order to remove this background, we can simply ask only for a prediction that do not raise warning flag. And we see that directly we are conserving many correct prediction, but removing this smooth background. And actually, if we require flag QSOC be equal to 0, we have that 97.6% of the prediction are correctly predicted. So I consider here that a redshift error that is lower than 0.1 is not catastrophic. Also now, if we look at the uncertainties that are associated to this result, so I'm considering only here sources that have an absolute difference, an absolute error that is lower than 0.1. Simply because otherwise we will have very, very large data. These are what I call catastrophic features. Prediction, sorry. And we are looking actually at the distribution, normalized distribution of the error, the logarithmic error. So just remember, this is this formula divided by its uncertainties. The uncertainties on the logarithmic redshift error, you can retrieve it quite simply from this formula. We'll not enter into the detail, but actually what we see is that the distribution of the prediction approximately follow a quite nice Gaussian, standard normal Gaussian, since we have a mean value of 0.007 and a sigma that is very close to 1. And the same also apply if we consider only prediction without warning flags. So we have quite confident prediction and good uncertainties that are associated to this prediction. Now, let's see how to properly use the QSOC result. There is obviously the first thing that came in mind is just there should be dependence on the G magnitude, roughly on the signal to noise ratio. What we see from this plot is that around 90% of the sources with G magnitude that is lower than 19 here have an absolute error on the redshift that is lower than 0.1. So this is the black curve. Now, if we are considering faint sources, so between 19.9 and 20, we see that actually this fraction is much lower and is only obtained if considering sources that do not raise warning flag. So this is the orange curve. Unfortunately, only 5% of these sources do not raise warning flag because there are a lot of ambiguity and so on. Also because the spectra are poor quality. So this is very low, actually. So instead of doing this sharp cut, we should consider instead also sources that have poor quality spectra. So as a reminder, this flag, this is the bad spec flag, warning flag, whose value is 16. And that is raised only if we don't have sufficient number of transit, much lower, much higher magnitudes or faint magnitudes, or a combination of both. So lower quality spectrum. But if the QSOC flag is equal to 16, this means that we do effectively have poor quality spectra, but we were still able to derive a proper redshift. So meaning we don't have ambiguity, we have a good Z-score, we have a good chi-square ratio, and we selected the optimal peak. And if we are looking now at what are the predictions, we have that if we consider, so then the flag equal to 0 or 16, we have that 92% of the sources in the redshift, the magnitude range 19.920 do have a good errors on the redshift. And this concern now not anymore 5% of the sources, but 36% of the sources, which is much better. We have much more sources and still have a very good prediction. If we are going further, actually, we can even look at some of the faintest sources that Gaia is processing. So meaning between 20.4 and 20.5. We see that we have virtually no sources that do not raise warning flag in this range. While if we are looking at both kind of flags, 0 and 16, we have that roughly 80% of the sources still have good prediction. And this concerns one sources out of 5, so 20%, in this magnitude range. Now, another way of looking at the QSOC result is to look at the completeness. What I'm told the completeness is the fraction of sources that have an absolute error on the redshift that is lower than 0.1 with respect to the literature value. So this is what fraction we are recovering for given true redshift actually. And we see that we have two band, lower band here, that are associated to redshift around 2. So this is a quite classical mismatches between the carbon-4 emission line and the Lyman alpha emission lines, because the shift between this lines and carbon-4 and carbon-3 emission line are quite comparable on once considered on the logarithmic scale actually. And the other one was quite surprising for us as this lower band in the redshift range 0.9 or 1.3. And actually this is due to the sole presence of the magnesium 2 emission lines in this redshift range. Again, we see that if we are setting some cuts on the warning flag, those shortcomings start to be alleviated. So if we are looking now at red stream spectra, so here each row in this plot, I'm considering bin for redshift, and I'm binning, taking the average of the spectra in this bin, set into a stream. So this is what Gaia is observing actually. This is derived from this paper where it is instead plotted in observed wavelengths. And we see that in the range 1.9, 1.3, only the magnesium 2 emission line is covered. So the magnesium 2 emission line is covered. So the carbon 3 emission line is not yet entering, and the H beta already left. So the sole presence of the magnesium 2 emission line has some deleterious effect of increasing the rate of mismatch between this line and the Lyman alpha. So we see here the Lyman alpha that is fitted to the magnesium 2 emission line and the H beta emission line. So now it's quite simple to think, okay, yeah, here we can see a carbon 3 emission lines. Well, maybe the H beta emission line, here the carbon 3 emission line, maybe H gamma, something like this. But if I provide you with the sole observed spectra, I'm wondering what will be the prediction by eyes, just by eyes, just guess. Actually, for this spectra, we only have one emission line. And here are wiggles. This is noise that are modeled by the internal representation we are doing in Gaia. As a consequence, we are making a lot of false prediction, very low redshift range if H beta is fitted to the magnesium 2 emission line, and very high redshift region if the Lyman alpha is fitted to the magnesium 2 emission lines. Another issue also arises very close to redshift of 1.3. As now the carbon 3 emission line is entering the spectra, we see it clearly. But the magnesium 2 lies on the peak of the BP spectrum, where actually this is an issue. It is systematically wiped out from the mean spectrum representation. So we again have only one emission line, that is now the carbon 3 emission lines. And we have mismatches between the carbon 3 emission lines, the Lyman alpha, and the magnesium 2 emission line that is taken, the carbon 3 emission line that is taken as the magnesium 2 emission lines. But for example, here again, we have wiggles in them that are fitted H beta actually.
Sorry, Ludovic, time
Yes?
check is 9:48.
Okay. I will try to speed up. So there are also purity issues with the predictor. The redshift, the best purity is in this range because we have Lyman alpha, carbon 4, carbon 3, and magnesium 2 emission lines together. But again, cut can alleviate the shortcoming. And we have lower purity in the border of the spectra simply due to the fact that in very, very low and very high redshift quasar are rare. So as a summary, I remind you that QSOC aim to be complete rather than pure. So for the source process, the purity can be achieved using this selection on the DSC drawing probability, or giving the receivers that are used in the extragalactic content paper. There are the generalities that exist between the predicted redshift over some redshift ranges that are comprised between 0.9 and 1.3 due to the sole presence of the magnesium 2 emission lines, and around redshift 2, so mismatch between carbon 3, carbon 4, and Lyman alpha. These are more frequent amongst faint sources, and cut on the flags, warning flags, discarded as a wrong prediction. We saw that the requiring that flag, warning flag equal to 0, lead to large amount of prediction that are discarded. This can be fixed for faint sources using also the flag 16. Now, two points we did not mention is that QSOC is designed to process type 1 core-dominated quasar. So it will yield wrong prediction, or poor prediction, at least on galaxies type 2 AGN, blazars, and so on. But in any case, we'll have warning flag non-zero. And in Gaia DR3, this is more technical, but we did not add access to the full covariance matrix on the BP and RP flex. So we are wrongly estimating the chi-square solution that is systematically underestimated. And this is the reason why we are not publishing it. After we are rescaling the confidence interval, they may still sporadically suffer from this limitation. So now, what are the future plan? In Gaia DR4, starting from Gaia DR4, we will use epoch BP and RP spectra. This allows us to take the variability into account, to have sharper spectral features, to have uncorrected noise and flex, to fix some wiggles issues I briefly mentioned, and there are also internal DPAC benefits. We'll use priors also that based on the quasi-luminosity function. This will allow to lift up many degeneracies between predicted redshift. And there will also be potentially new astrophysical parameters to be derived. So we are doing some validation now just to see if it's worth the pain if we can derive them actually. So this means the continuum slope, the balancity index, the emission line total equivalent weight, absolute magnitude, maybe the second or third most probable redshift. And that's all.